Welcome back. So in the last class we have started our discussion on AC/DC converters and their control, and we have understood what are the different methods of controlling them. First we have seen the square wave modulation, where the switches will be operated at fundamental frequency. The limitation was it had high amount of harmonics and it does not have any ability to change the output AC voltage. Then we have shifted to quasi square wave, where again it is in fundamental frequency operation, but what is the difference over here? Here we will be able to regulate the output voltage by changing a zero duration. So for a fixed DC voltage we can have variable output AC voltage. Then we have seen multiples. This addresses the limitation of this quasi square wave, that it has high amount of harmonics. In multiples we get relatively less harmonics and we will be able to regulate the output voltage also. But what if I want to eliminate the harmonic such that we do not require any additional filters? So we go for pulse width modulation techniques, where we will be having an high frequency switching operation by using an carrier wave compared with sine wave. In that we have seen this subcategory, that was our Sine PWM, and how this is done. Then we have shifted into our three-phase BSI, where we have seen the fundamental frequency operation, which are called as 120 and 180 degree mode of operations, which we will be seeing now. So here in this 180 degree mode of conduction, each device will be conducting for 180 degrees. Whenever one switch turns on, it remains on for 180 degree, and for the remaining 180 degree it will be off. So if you see the number of commutations in this 60 degrees, after every 60 degrees which are marked over here, after every 60 degrees we get one commutation, that is there will be one switchover of device. So here in the VRO voltage, if you see, switch 1 and 4 are conducting alternately. So this is the voltage of this point with respect to the neutral point. So when switch 1 is on, when I apply the KVL and try to find out what will be the voltage between this VRO, I will see that it will be equal to plus VO by 2. When the vice versa condition is true, that is S4 is on, I will get minus VO by 2. So in this way we will be able to generate a square wave. So in 180 degree again we have square wave operation, but it is in three-phase circuit. So here now what will be the limitation of this one? Again we will be having the limitation of high amount of THD, the harmonics will be at the lower end. So it will be creating a huge issue with our load. So we will be requiring external filter if you go for this type of circuit. And in this case these are the line voltages. So if you see the line voltages, we have three levels, that is plus, minus and 0. And in this case again with the DC link voltage my output voltage gets fixed, and there is a possibility of commutation failure between S1 and S4, that is when both of them are triggered simultaneously we will be having an short circuit fault. So in the olden days this was a critical challenge, but nowadays although we do not have any major challenge in operating switches in complementary way, but then after that in the olden days we have shifted to here 120 degree mode of operation to avoid this issue of commutation failure. So in this case if you see what changes has been done, now the duration of conduction has been reduced from 180 to 120 degree, and we have an zero voltage duration of 60 degrees, which can be used to commutate your device so that the commutation failure possibility is eliminated in this case. Okay. So here what will be the limitation of this 120 degree mode of operation? Again as I say, 120 degree mode of operation, the conduction duration of the switch is constant, so my output voltage becomes constant. Again we will not have any flexibility of regulating the voltage. So this will be the line voltages. So we have R, B and G, which are denoted with the respective colors. So the three phases and the line voltages. Okay. So what is the line voltage? So VRB will be equal to the pole voltage VRO minus VBO, and so on. Then we have started our discussion with our Sine PWM, where we have gone for unipolar and bipolar for the single phase circuit. Now we are discussing about the three-phase circuit. So in this three-phase circuit we will be requiring three modulating signals or three sine waves, so which are shown over here. So if you see the difference between the three sine waves, they are phase shifted by 120 degrees from each other, and they are compared with an high frequency carrier wave. The comparison logic remains the same, that is for A phase or the R phase, so as to say the R pole, so which generates the A phase AC output. So in this case this red triangle, that is A reference, it will be red sine wave will be used to compare with the carrier wave, and based on that And based on this logic, that is, whenever my reference signal is greater than the trigonal signal, I will turn on a switch which will apply positive voltage, that is S1 over here. Okay, the moment I turn on S1, my voltage at this node R will be shifting to VO by 2. So, in this case, when the complementary condition is true, I will turn on S4. Similarly, for the B and C phase, the same logic is followed, but if you see, the reference has been changed to B and C phase references, which are phase shifted by 120 degree from each other. Now, in this case, what advantages we get? So, among the methods which we have discussed till now, so this is the best method in terms of the TAT performance. We will be able to regulate the output voltage and frequency. Okay, so why the frequency modulation is required? Although we say that our grid is rated to have 50 hertz, but due to the mismatch between your load and generations, you will always see that the grid frequency will be slightly varying. So, how to change this frequency of this output signal over here, or the AC voltage which is generated by our AC to DC converter? We will be changing the frequency of this modulating signal. Okay, so if you see, we have not marked the time axis, so it depends on the what will be the total duration of this. So here, if you see, it completes one cycle, so it will be 1 by frequency, that will be the time duration. The moment I change this time duration or the frequency of my modulating signal, the same frequency of sine wave will be generated across the A terminal, and so on. If I adjust the B phase modulating signal frequency, then it will be changing the B phase and C phase. Okay, so as we are assuming balanced three phase supply, always the frequency will be changed in all the three phases simultaneously. Suppose I want to change the output voltage, so what will be done? Now I have to adjust this height of this modulating signal. Okay, so the frequency of my output signal will be equal to the frequency of modulating signal. The amplitude or the magnitude of output will be proportional to the amplitude or the magnitude of my reference modulating signal. The moment I change the amplitude of this one, it will be changing. So here in this case, what will be the whichever thing we have said, that by changing the amplitude of my modulating signal, I will be changing the output magnitude. It is true till the converter operates in linear region. What is the linear region? The modulation index or the ratio of your modulating signal to the BDC by 2. If it is between 0 to 1, it will operate in the linear region, or our output will be AC output will be proportional to the magnitude of my modulating signal A reference or B reference till the value is limited between 0 and 1. Okay, so what is MI modulating index? It is the ratio of the output AC magnitude or the peak of that one, okay, to VO by 2, or 50% of the DC link voltage, which can be the maximum voltage it can generate in the positive direction. So its value should always be less than 1. Then I will be operating in the linear region of this. When I go beyond 1, I will again come back to my dominant harmonic at the lower hand side, and our converter performance will be deteriorating. So always we will ensure that the MI is set between 0 to 1, or the output voltage is regulated between 0 to V0 by 2. We are talking about the peak of that one. By root 2 times of that, that will be giving me the RMS of my output voltage. Okay. So what is the use of this variation of voltage and the frequency of the output AC signal? So that we will understand by an example. Here we have considered that we are using this active front end converter, which is fed from a DC source, to drive an induction motor. So in place of the AC supply, now we are replacing it by an induction motor, and it is controlled by classical control technique, that is V by F mode. When we go into the machines, we will see what is classical control mode and why this V by F is maintained constant. So for time being, we will assume that we are having a control technique for the induction machine, where we are trying to maintain the ratio between the voltage and frequency at a constant value, and initially it was applied with the rated voltage and frequency, that is 400 volt and 50 hertz. Now due to the requirement of variation in the speed, I want that the supply frequency to be reduced to 40 hertz. So what will be the requirement for the voltage? That's what is the question over here. So why this B by F is maintained constant? So it gives us constant flux in the machine. Okay, so what is this constant flux and what is B by F method? We will come back to this in the next few lectures. So for time being, now if I want to maintain this V by F as constant and I want to calculate the output voltage, what will be that? So if 400 by 50 is to be maintained constant with X by 40, so I will find out that my V2 will be equal to 320 volts. Okay. So why we have put this example over here? To understand what is the meaning of changing your frequency and output voltage. So here I want to change the output voltage to 320 volts, okay, and the frequency to 40 hertz. Okay. So we have 20% reduction in both the quantity. So how this 20% reduction will be done? So let us go back to the previous slide where we have seen this. Now the amplitude, suppose it was previously 400, now I have to reduce the amplitude to 320, and the frequency, that is 1 by 50, that will be the time duration of the signal. Now I will change it to 1 by 40. Okay. So that is what only change I have to make to have this B by F control method implemented in this active front end converter. Okay. So here I will be just changing the frequency from 1 by 50 to 1 by 40, or the frequency of the signal will be adjusted to 40 hertz, or the time will be reduced to 1 by 40, and the voltage will be reduced from 400 to 320. Okay. Now from this discussion it is clear that by using Sine PWM we are having flexibility of controlling the output voltage and frequency, as well as we have shifted our dominant harmonic towards an higher end side. So the effect will be very less, as most of our loading will be inductive in nature or machine loadings. So as we have machine type of load, they will be having inherent inductance, so which will be sufficient to filter out the harmonics, or if we require an additional filter to filter out our harmonics, their size will be very less. The size of passive filters will be proportional or dependent on the frequency at which they are designed. If higher is the frequency, less will be the size of your filter. Now we are discussing about our closed loop control, where we have started our discussion on the projection theory, where we have seen that we have three quantities which are required to be controlled to decide our two factors, that is active and reactive power, which is exchanged by this converter. We have two control requirement, that is P and Q. They will be bidirectional, as this is an active converter, so I can control the active power flow as well as reactive power flow in both the direction, that is it can be supplied from the grid or it can be absorbed from the grid. So here we have three AC quantities. Now I want to control only two variables. Can this done in a better way? So we will be trying to change these three values into two values, so that two control parameters will be directly dependent on these two quantities, or the two control parameters, one will be controlling active power, one will be controlling the reactive power. So now for example, so understand what will be the projection of these three sinusoidal quantities on an reference frame, which we are assuming it to be as shown in the diagram. So VA will be equal to, if I assume omega t is equal to 90 as an example, at that point my VA will be having its maximum magnitude, that is Vm, because sin 90 will become 1. Then this will be my Vb and this will be my Vc. So when I try to find out the resultant, I will see that it will be having a magnitude of 1.5 Vm and it will be aligned across the x-axis. Now next example, where we have considered the omega to be 220. So if I replace this omega t by 210, so it will be giving us the values, where again the magnitude will get constant to 1.5. And as a next example, where we have 330. Okay. So at the omega t equal to 330, then also we will find out that the magnitude will be moving ahead, but the resultant magnitude will be constant, although it has changed its angular position from omega t equal to 210 to omega t equal to 330, but the magnitude is again constant at 1.5 Vm. So if I consider other values of omega, I will see that always the magnitude will be fixed at 1.5 Vm, and it will be continuously rotating at, and the resultant will be rotating at a speed which will be equal to the speed of my, or the omega of my sinusoidal signal. So what will be the speed of this resultant vector? It will be again rotating at omega t. So the moment my supply sine wave will be completing one cycle, my resultant vector will also complete one cycle. That is what is the meaning of this one. Now if this rotating resultant value is observed from two stationary frames, okay. So if I have two stationary frames, one will be denoting as alpha, one as beta. So they are called as your stationary reference frame or alpha beta reference frame. So this alpha beta frame has got the standardized name. So when I say alpha beta, we should understand that it is a stationary reference frame. What is the meaning of stationary reference frame? It is not rotating, it will be fixed irrespective of your omega t value. The location of your alpha and beta axis will be same as shown in this slide. So now if I observe this rotating vector which we had a magnitude of 1.5 and I see the projection of this resultant vector in alpha and beta axis, I will observe that I will get two sinusoidal quantities. It will be exhibiting an sinusoidal motion as simple harmonic motion over here, SHM, and this is how I will obtain two quadrature components. Okay, so why this quadrature component is important for us? So when I have some variation in beta, so it will not affect my alpha frame. When I have some variation in the parameter with respect to this alpha frame, it will not affect the beta. So whichever quantity is there, may it be your voltage or current, if I am trying to change the current or voltage along the alpha axis, it will not affect your beta axis. So that's why we are interested in quadrature components. So now in this alpha beta axis, if you see, now we have this resultant vector. Now this resultant vector, if I try to calculate what will be the value in terms of your V, A, B and C, what does where our supply or input voltages, I will see that V alpha will be given by V A minus B B by 2 minus V C by 2, and V beta will be given by this relation. Okay. So if you see it is or observe the alpha and beta values over a cycle, I will see that I will get two sinusoidal components. Those will be separated by 90 degrees from each other. So our first purpose that we had three independent voltages which were to be regulated to control two parameters, that was our active and reactive power. Now we have successfully reduced these three variables into two variable systems. Now but what has happened, as I said, this alpha and beta which is there, they are not an fixed quantities. Okay. So why we want be DC quantity or fixed quantities? The PI will be having a better tracking efficiency when we go for DC quantities. So here in matrix form, so this alpha beta transformation is called as Clarke transformation. So this is the matrix for that. Okay. So in this I will be replacing my VA, BB, VC, and I will be finding out two orthogonal components or two quadrature components which will be independent from each other, but they are still AC quantities because they are having variable in nature or their instantaneous value will be changing based on the omega t. What is the solution for that? Suppose I want to have two quantities, but they should be fixed or they should be at DC value. So for that we will just make a small change. Instead of stationary DQ frame, stationary alpha beta frame or stationary frame of reference, we will go into a rotating frame of reference. In this rotating frame of reference, if you see, they are denoted by D and Q, where alpha and beta is for stationary frame, D and Q are for rotating frame. They are standard names given to the frame transformations respectively. So in this D and Q, if you see, now this it will be rotating at a particular speed. So what was our aim of rotating this frame of reference itself? To have two DC quantities. Okay. Suppose this resultant is rotating at an omega t and I want its projection to remain constant. So what should be the speed of this one? So it is very clear that it should also rotate at the same speed, so that if the resultant vector moves, the axis will also move, so their projections will become constant. So theta must be equal to your omega t, then your delta will become equal to 0 if they are rotating at the same speed, and we are considering that they are aligned across the d axis or the resultant is aligned across the d axis when omega t is equal to 0, then we will see that they will always, your d component will have a finite value and q component will always have a 0 value. So we will get two DC values over here. Okay. So how to go from or shift from your alpha beta frame to your DQ frame? So this is what is given over here. By following this relation, we can map our alpha beta frame values into DQ frame or the rotating frame values. So BQ will be given by minus B alpha sin theta plus B beta into cos theta. Okay. So how this has been derived again from the projection theory. Okay. So we have alpha and beta. Now we are trying to calculate the projection of this on an rotating frame of reference which is rotating at a speed of omega t. So in this case, if I go for the matrix, so this will be the matrix which will be used to transfer your alpha beta axis into your DQ frame or DQ axis. Now if I do not want to go into alpha beta frame, now directly I want to go into DQ frame, because I know that alpha beta frame will give me two sinusoidal quantities, which is not of much interest for me. I want to DC quantity, so directly I can shift from your ABC frame to your DQ frame, or from the ABC or our actual supply voltages, we can go into our rotating DQ frame by using this matrix. Okay. So this transformation is called as your Clarke transformation, and this is not the unique way of denoting the matrix. Okay, so the values over here can be changed. This multiplying factor and the zero vector value, this can be having various values depending on the type of Clarke transform we are using. Okay. So here we have considered one particular example where we have 2 by 3 as our multiplying factor and half as my third quantity. Okay. So here if you see, we have the result of two quantities, but here we have the third variable. Okay. So here it will be V0. So what is V0? So V0 is your zero sequence component, which comes into picture when we have some type of unbalance and we have four wire system. Okay. So in three wire system, generally this will be 0. So we are not considering that over here. In our discussions, we will be mostly concentrating on our balanced three phase supply. So the resultant of this one, or the VD and VQ, will be of importance for us. So that's what we are considering in this. So what is the significance of our DQ frame? Now in this DQ frame, we have already discussed that it is a rotating reference frame. It rotates at a speed of omega t, and DQ frame is also called as a synchronously rotating reference frame. Why? It runs at the same speed of our supply voltage. So we say that it is synchronous reference frame, and VD component is same as the resultant vector. Why? We are assuming this condition to be our initial condition, that is our resultant vector is aligned across the d axis at omega t equal to 0. That is what we have assumed. So that is why our Vd will be the magnitude of across the Vd axis, the DC quantity will be having a value of equal to the resultant vector. Okay. Vq will be having 0 quantity. Why? If you see at this point, what will be the projection of this one? So it is having 90 degrees. So obviously the projection of d on q axis will be 0. Again, will it be or always be 0? The answer is no. It can have some other values if we are not having balanced three phase supply. Okay. Now change in Vd will not affect Vq. Why? They are having 90 degrees apart from each other. We have two orthogonal vectors. So if I change something on d axis, it will not affect anything on the q axis, and if I change something on q axis, it will not affect your d axis. For example, in this case we have considered Vd and Vq. So if I change Vd value, it will not affect Vq. If I change Vq, it will not affect Vd. Now Vd and Vq are constant DC values. Okay. So they are constant. Why? Because of the frame which we have considered, that is it is rotating reference frame. The three phase dependent quantities, that is your VA, VB, VC, we had three variables. Now we have changed it into two independent variables, that is two DC quantities. So the performance of your conventional PI controller, which is the most popular one we use in our applications when we go for grid connection systems. Why we go for PI controller? Because in PID performance wise, PID is the best controller in these three controllers, that is PE, PI and PID. Among these three, PID will be the best one. But why we restrict our application to PI? Because in this case, if you see, we are having grid connection of the system. So the poles and zero, or the model of the grid, is constantly changing. So we cannot have the particular value of pi, or we cannot have the design of model of our system. So pi values has to be fixed arbitrarily or by having hit and trial methods. So for that, if I have derivative, what will happen? So it has derivative controller is sometimes called as your anticipatory control. It tends to make our system oscillatory, so it can create some issue with our stability of the system, because we do not have the exact model of our system. So generally we prefer your PA controller for the application where we do not have the exact model of the system. Okay, so where we go for PID? For a drives application. Suppose we are designing an AC to DC converter which will be present on the board of the vehicle, or it will be running with the vehicle, where we generally have AC machines like your induction machine and PMSM. So there I can go for PID, because once the machine is designed for the lifetime of the vehicle, it will drive the same machine. So there I can have particular value of your poles and zeros based on the machine which we have used. So I can go for PID, but for grid connections we generally go for PI. So in this PI, if you see what is the performance of this PI when I use it in the AC quantities or when I use it to track AC quantities. So what is the control system? It generally tracks two quantities, our reference and the actual values. It calculates the error, and its aim is to make our error 0, or the steady state value will be equal to the reference signal which is provided. So if I say PI is performing in better way, so the moment I change my reference, it will take very minimal time to go to the new reference value. So when I operate the same PI for AC quantities and DC quantities, I will see the response or the performance of my PI controller will be better when I give DC quantities to it. Okay. So what are advantages which we have got by shifting from your ABC frame to your DQ frame or the synchronously rotating frame? That is, first we got two independent quantities and two DC quantities. So the independent, it means when one is affected it will not change the other quantity, and DC quantity, it makes the performance of our PA controller better. So now here let us see what is the closed loop operation of this converter. Okay. So in this active front end converter, when I say closed loop, so it can control the flow of two power quantities, that is active and reactive power. Okay. The active power will be used to charge or discharge your vehicle for V2G or G2V operations. Reactive power will be used as an power quality parameter. So it can be used to maintain the voltage magnitude at the point of common coupling or the point at which we are connecting the charger. Okay. So here in this closed loop, if you see, all the voltages are dependent on each other. Why? Because we want balanced supply. We do not want to go into unbalances in the supply or in the output of our AC, okay, terminals. So at the output AC terminals, we do not want unbalanced, or we do not want to have unbalanced grid operation. So in that case, we will be having three variables. Now by using this Clarke transform or the DQ frame transformation, we have successfully decoupled them into two parameters. One will be responsible for controlling active power, one will be responsible for controlling the reactive power, which you will see in the next slide how they will be done. So what are the advantage of this one? Output voltage regulation to a desired value. So based on my active and reactive power, my voltage can be adjusted. Okay. So on what, how these two parameters will be decide my voltage magnitude. So we have also discussed this. So we can consider we have the AC grid on one side and our converter on the other side. Now if I want to control the active power flow, I have to change the angle. So whichever direction of power is required, I will make that lagging or leading with respect to the grid. Okay, so we consider the grid as our reference signal and adjust our output voltage which is generated by our active front end converter. Now reactive power, how this reactive power will be controlled? By changing the magnitude of the voltage. Okay, so the magnitude of the voltage generated by my converter has to be changed. If I generate a higher voltage with respect to the grid, I will supply reactive power into the grid. If I generate a voltage whose magnitude is slightly less than the grid magnitude, so I will consume reactive power. So whichever is having a higher magnitude, it will be the source of my reactive power. Based on my requirement, I can change the voltage and its phase angle to adjust the active and reactive power. So what is the importance of this frequency? That also we have discussed. The supply grid frequency and the voltage generated by the converter should have the same frequency, because we want synchronization operation, or we want to have the same frequency on the converter output as well as on the grid side. Okay. Now fast dynamic response, if something of changes or some parameters changes by some due to some transients or due to the normal wear and tear of the circuit, it will be able to adjust itself and the dynamic response will be better. Satisfactory disturbance rejection, if there is some type of disturbance, most of the time our closed loop controller will be able to handle it by itself. Reduce steady state error. So what is the meaning of steady state error? In our application, if I set a particular speed reference for the motor or for the vehicle, so it will be obeying that, or it will be running at that particular speed. So that's why our steady state error should be as minimum as possible. So in this case, in the closed loop, we will get the minimum steady state error, because we will be mostly using PI or PID controller. In both the cases, our steady state error tends to 0. Current drawn at UPF, if I do not want to support the grid or consume reactive power, I can set it to 0 conveniently. There will be not any issue with our B2G or G2B operation. The power, active power, can be perfectly changed independently with respect to the reactive power. Although it is 0 or some finite value, irrespective of that, I can independently change my active power. Okay, so that's why we have gone into this DQ frame, where we have independent control on active and reactive power. They are perfectly decoupled from each other. Now, what will be the model of this system if I want to map this active front end converter into my DQ frame? So, before that, let us understand what will be its model in the ABC frame. So, here this is the first equation is for our A phase. Okay. So, this LDI A by dt plus RIA will be equal to the difference between the grid voltage and the converter output voltage. Okay. So, what is this one? If you see, these are the inductance and resistance between the grid and our converter. They can be your filter inductance or the inductance offered by your transmission line, or the equivalent grid inductor value and the respective resistance value. So, now this drop in this will be responsible for this IA current and difference between the two voltages. Okay. So, why we will get this drop? Because there is a difference in the voltage. So, there will be a particular value of current, and we have an impedance in the path. So, we have an AC supply. So, our inductor and resistance will be consuming this amount of voltage, and that will be equal to the difference between the voltage on the two side of the impedance or the resistance which is present over here. Okay. So, here what is the value of BA? It is fixed, it is an sinusoidal AC quantity. Now, how we have got the voltage at this point R? So, it is written as S1 minus S4 V0 by 2. Okay. So, if you remember our Sine PWM technique, we have said that we will be turning on S1 when I am having the modulating signal amplitude higher than the carrier signal. The when by vice versa condition is true, I will be turning on S4. Okay. So, suppose I am turning on S1. S1 and S4 are perfectly complementary to each other. What is the meaning of that? If S1 is on, it means S2 will be off. Okay. So, generally these are the switching signals. They will be either 1 or 0. 1 it means the switch is on, 0 it means the switch is off. So, in the first cycle, that is in the first case where my modulating signal, suppose it is greater than my triangular signal, I will be turning on S1. Okay, so what will be the status? S1 is on, so it will be 1, this will be 0. What will be the equivalent expression of this turn? So it will be giving me V0 by 2. How this V0 by 2 is coming into picture? If I turn on S1, so it is as good as this point is connected to the top bus, neglecting the resistance drop of switch S1, considering S1 to be ideal switch. So, R will be connected to the positive bus. What will be the potential difference between VRO terminal or with respect to reference ground? So, it will be equal to V0 by 2. That is what we have got from this. Now, suppose the complementary condition is true, my switch 4 is on because my modulating signal, it is greater than, modulating signal is less than the triangular signal, that is triangular is having a higher amplitude. At that time of I will be turning on S4, so that negative voltage is applied. So, minus, if I see the resultant of this one, it will be minus VO by 2. With the same cable, I will be seeing that point will be connected to the negative bus, and my VRO potential in this case will be equal to minus V0 by 2. That is what we have written in terms of this S1 and S4. So, they will be replaced with, and status of 1 when the particular switch is on, they will be replaced with 0 when the particular switch is off. Similarly, for the B phase, the same set of equations, but the corresponding values of the switch has been changed, that is S3 and S6. Then for our phase G or the C phase, we have this S5 and S2. Now, if I have got three set of equations, now if I change it into DQ frame, that is my rotating reference frame, I will see that it will be giving me this equation in the D frame. Okay, so if you see all the quantities are having D frame values. So here why this Q is there, we will come back to it shortly. So here if you see the compare these equations, if you see, we have got MD into V0 by 2. What is this MD? It is the modulation signal in the DQ frame, MI value in the DQ frame. Okay, or the modulating sine wave. Okay, so it will be containing the information of this MD value. Okay. So it's the modulating signal. Now we have got minus Vd, so which will be got from these three terms. Okay. Then we have the two drop terms. Now if you see why we have gotten Q term over here. Okay. So what was our aim in shifting into our DQ frame? We wanted perfectly decoupled quantities. But here if I derive the model of this active front end converter in the DQ frame, so this will be the Q frame quantities. Okay, so in both the cases, if you see in the D axis I have got Q axis current, and in the Q axis I have got D axis current. Okay, so it is because of the inductor which was present in between. So because of that we have got an type of coupling between them. So what is the meaning of that? If I change the D parameter now, it will slightly affect my Q parameter because of these two terms. So now we will slightly modify this such that these terms are perfectly decoupled from each other. That is, D frame will be perfectly decoupled from the Q frame. We see that to be your cross coupling terms, and appropriate adjustment will be done in the closed loop controller so that the effect of this cross coupling is eliminated. Okay. So if you see if I map this same two quantities in the active and reactive power, which are our two control parameters, I will say it will be 3 by 2 BDID now and BQIQ. Similarly, QS will be equal to BDIQ and BQID. Okay. So here in this case, if you see again, because of this cross coupling terms, we have got two other terms which are cross coupled to each other. In this case, if you see, suppose I am giving the power active power control to the D axis, I have got an Q axis term over here. Although its magnitude will be very less, but still we have an coupling between them. So how to decouple this one? So for this decoupling, we will provide the appropriate compensation. If you see, the compensation amount is equal to the terms which were present in our equations. Okay. So this is our closed loop controller diagram, where we have the reference D frame current. It is compared with the actual D axis current. The reference value with the actual value is compared over here in the Q axis also. The error has been passed to PI. Okay. So we have PI controller which will be getting error at the input, and it will be generating an reference voltage at the output terminal that has been feed forward. So these two are a feed forward terms, so which we are giving to increase the response of our system. And these two terms we have already discussed, they are the decoupling terms. If those are absent, there if I change the active power, it will slightly affect my reactive power. So to eliminate this cross coupling, we have provided this decoupling terms. Okay. Then we are changing it to per unit values by dividing it by the value of BDC by 2, or 50% of our DC link voltage, which we have denoted as VO also. Okay. So 50% of your DC link voltage, which is the maximum voltage it can obtain in the linear region, which we have already discussed. So that we are dividing such that its value will be restricted between 0 to 1. Okay. So it will be two quantities, one will be on the D axis, one will be Q axis. When I again go for the reverse Clarke transform to find out the value in the ABC frame, I will get three modulating signals MA, MB, MC. Now what will be the relation of this MA, MB, MC? So they will be perfectly balanced, that is, they will be having a phase shift of 180 degree from each other, and they will have a particular amplitude and angle shift based on my active and reactive power reference. So we will continue from this point in the next class. Thank you.